contamination. This is joint work with Serbi, my advisor Adam, Abhishek, Kevin and Arsene. And this talk will be primarily based on these two papers. So I work on reliable learning theory. So I want to prove strong guarantees for learning algorithms. And the first question to ask when you're trying to do that is, of course, how can you model the input of the learning algorithms? So even that is not trivial for learning theory. What is the input? And the reason is that training sets are usually of low quality, or the actual training sets, or even contain malicious content and so on. So in practice, data distillation is actually a crucial part of the training pipelines. But here, the question we ask is, how does contamination influence the complexity of learning? So we care about the computational complexity. And this is actually a very old question. It dates back to the 80s. So one formal model, standard formal model that is used to study this problem is learning with nastiness or bounded contamination. And there should be a green disk here. It doesn't appear, but anyway, so that's the clean distribution that generates pairs x, y. X comes from some distribution that is nice, it's structured, like the Gaussian distribution, some very nice distribution. And the labels y are generated by some function f star that lies within the class that we want to learn, some constructors. Okay, then a bunch of phi-ID examples, clean examples are generated. And then an adversary sees these examples, removes an eta fraction of these examples, and substitutes them with an arbitrary equal-sized set of pairs x, y. So, remove eta fraction and substitute them with another eta fraction that is arbitrary. Both x and y are arbitrary. So the learner receives this contaminated data set, and then it is asked to output some hypothesis h, whose error on the clean distribution will be 2 times eta. Okay, and this factor of 2 there is actually necessary, as it was shown in the paper that defined the model. Essentially, the idea is that you pay eta for the things that you don't see, and you pay eta for the things that might force you to make mistakes on the rest of the clean examples. Okay, but this is bounded contamination. We can there's some space here, and what we can put here is learning with heavy contamination. So this is a new definition. Once more, there is a clean distribution, but now we will not assume anything about the labels. But just x is still structured, comes from some nice distribution, but y is we don't assume anything. And the reason we don't assume anything is because even if we did, nothing would change. So let's see what do I mean by that. So once more, a bunch of IAD examples from the clean distribution are drawn. And then the adversary sees these examples and adds a large number, maybe 10 times more than the clean examples, of arbitrary labeled examples, x, y. Okay? And the budget now of the adversary is measured with respect to Q, which is the contamination ratio, which is essentially the size of the whole contaminated data set, both adversarial and clean, divided by the size of the clean data set. So that's Q. So if Q is 2, then 50% of the data are clean. So this is seems more like actual data sets, right? So anyway, so what is our error benchmark here? So let's define this quantity opt total, which is the minimum error. So we still have a class that we wish to learn, okay? And the benchmark with respect to this class is opt total. What is opt total? Opt total is the minimum error rate that some hypothesis in F can achieve for the whole input data set with contaminated samples. So it's number of mistakes on the whole input data set by the best classifier in the class, divided by the size of the whole input data set. That's opt total. But the learner is asked to achieve this type of guarantee. So we have to output a hypothesis whose error on the clean distribution is Q times opt total as epsilon. What is Q times opt total? Well, Q, as we said, is the number of all the examples divided by clean, and this is the number of mistakes divided by number of all the examples. So in total is number of mistakes divided by number of clean examples. So essentially we're saying, it's fine if the algorithm pays for all the mistakes made in the whole input data set as if they were made in the clean examples. And now this is actually tight. So you cannot do better than that. Even if the clean distribution was realizable. Does everything make sense so far? So yeah, please ask me questions if something makes sense. So yeah, so this Q times total is necessary, meaning let's say that the clean distribution is realizable, but the adversary can it can, let's say Q equals 2. So it can have as many adversarial examples. So these examples can have the opposite labels from the actual clean ones. And therefore the learner does not know whether the ground truth is F star or minus F star. So the error should be 1/2. Okay, even though under the clean distribution there is a perfect classifier. Okay, so this is necessary. I mean, I told you how to do this for Q equals 2, but even for larger Q, there's a lot of Okay, so these are the two problems, and one is standard, bounding contamination. The other is kind of a new definition, and the reason I put them side by side is that the same algorithm solves both. So let's see. So let's first convince ourselves that if we have a class that has bounded VC dimension, the sample complexity of these problems is bounded by some polynomial in the VC dimension. So just run the empirical risk minimization algorithm. Then what's the error of the ERM here? Well, we don't see these, but we see all these things. And now the error is, we can at most have eta times n mistakes. So the error is just eta. There of the ERM. So we can pay for this error on these clean examples. And then let's say we also misclassify them, like we give them all to the adversary. So in total we have 2 times eta error. And just standard uniform convergence will give you that you achieve that of 2 eta plus epsilon on the clean distribution. And similarly, by the definition of total, ERM essentially achieves the benchmark we set here. Because essentially we're just counting the number of mistakes. The number of mistakes the ERM is making here, maybe the adversary is so smart that made us make all these mistakes that we have to make. We make them on clean examples, not adversarial ones. And that's why we pay for all the mistakes in the clean examples. And that's why Q of total is the correct version. Okay, so in terms of sample complexity, it seems the problem is not that interesting, but we care about how contamination influences efficient algorithms, okay? And the idea is that, the crucial observation is that structure is very important for efficiency. Okay, maybe not for sample complexity, but structure in the input, like how X is distributed, is very important for efficient algorithms. For example, even if the additive error is constant, so we want to achieve some constant error, additive error, and the class, hypothesis class, the constant class is just the half spaces, which is one of the simplest classes to consider. Without further structure, if you want to output a half space that is an ERM for the data, then this is a bit hard. And in general, if you want to output just some hypothesis, this is cryptographically hard. So structure is very important, and contamination might remove the structure that we have. So what do we know about these problems? Let's start with adversarial label noise, which is a simpler knowledge model. And essentially, it's very similar to the bounded contamination. But now, the adversary can only change the labels. So the points x cannot be changed. The distribution of x is still this structure d star, but the labels y can be, an eta fraction of them can be changed adversarially. In terms of in this model, a sufficient condition for efficiency is the existence of low degree polynomial approximation. So if the unknown gram root of star can be approximated by a low degree polynomial under d star, which is the nice input distribution, in terms of the mean squared error, then we can get an efficient algorithm. And the efficient algorithm is actually polynomial regression. We just need to focus on finding the best polynomial, and this will perform similar to F star. So, moreover, this condition is actually necessary for if you consider that there is this class of SQ algorithms that is a very large class of algorithms, learning algorithms that essentially includes all known algorithms with very few exceptions, like Gaussian elimination. And in this model, this condition is actually necessary. So you need to have polynomial approximators. Okay, and just as an example, in terms of what kinds of upper bounds we can get with this approach, there are many classes. There are many, for many interesting classes, there are bounds on the approximation degree. Let's say, for example, that p star is the uniform distribution over the hypercube, then DNF formulas of size s have logarithmic degree, and monotone functions have sublinear degree in the dimension. Again, these are just two classes that are of particular interest for this talk. So that's what we knew for adversarial label noise. What do we know about bounded contamination? Again, these problems were defined back in the 80s, but all known results either have very bad dependence on the ambient dimension, D, or hold for very special classes and achieve suboptimal error guarantees. So the optimal error guarantee is 2 eta, as we said, but here the algorithms achieve something worse than that. In some cases, the error guarantee depends also on other parameters of the problem, like for half-space intersections, depends on the number of half-spaces in the intersection. But even to obtain these results, there are several very, very non-trivial ideas that are needed. But let's see, for example, for polynomial size DNFs, there's no quasi-polynomial time algorithm. Remember, the degree is logarithmic, so for adversarial label noise, we know that there is an algorithm with quasi-polynomial time. But here, for bounded contamination, we don't have such a thing. Okay. So this makes us wonder, is low approximate degree sufficient for learning of contamination? Okay, for heavy contamination now, there's no, to the best of my knowledge, there's no prior definition for classification. So heavy contamination has been studied, but either in the for linear regression or for unsupervised learning. But even in these cases, the results fall in these two categories. So the first category is list-decodable. Most of the results. So the list-decodable setting says, you will output a short list, and one hypothesis in this list will be guaranteed to be good. And the second category is semi-random models, where there is an adversary, but the adversary is monotone in the sense that it can provide more data, many more data in the input, but at least from an information theoretic perspective, this data only help information theoretic. They can break the assumptions that are important for efficiency, but other than that, they only help information theoretically. Well, here we don't fall in either of these categories. So first, we just have the single hypothesis, and secondly, the adversary can even trick us information theoretically. Okay? And we will see a concrete example. Okay, so that again makes us wonder, when is efficient learning possible under heavy contamination? So let's answer these questions. First, for bounded contamination, we showed that if you have the approximate degree is L, then you can just learn in P to the L, which is under bounded contamination up to error to eta, which is the optimal error. And this works for any hypercontractive D star. So apart from the approximation degree, we also use the hypercontractivity assumption for D star. And this nearly matches sufficient and necessary conditions even for learning label noise. So this like closes the gap between bounded contamination and adversarial label noise. And of course it implies new results for several classes. For some of them, the results are the first results. So for heavy contamination, the situation is a little bit more tricky. So instead of using polynomial approximators, any polynomial approximators, we will use this stronger notion of approximation, which is called sandwiching polynomials. And now, instead of having one polynomial that approximates the function, we have two polynomials. One of them is always above the function for all x, and the other one is always below the function for all x. But the expected difference between these two is small under the distribution, the target distribution this time. Okay? This notion originates to pseudo-randomness, and the reason it's useful there is that it's equivalent to fooling via moment matching. Okay, but we're not going to use this for this talk. What we are going to use is this result by Gregerman and subsequent improvements that says that the sandwiching degree of circuits of constant depth is polylogarithmic. Okay, so this captures DNA formulas as well. Okay, so our result here is if you have bounded sandwiching degree by L, then you can learn up to optimal error for Q heavy, under Q heavy contamination. And observe here that the sandwiching guarantee we actually require is not epsilon, but it is epsilon squared over Q. But even for Q equals 2, the problem is non-trivial. So let's just think about Q as a constant. Yeah.
If you have two sandwiching polynomials, then doesn't that also give you the approximating polynomial?
Yes.
Average them?
Yeah. You definitely. Each one of them is in particular an approximating polynomial.
But it's
because there is always between them.
Does it? Oh, it doesn't go the other way though, right? Like if you have an approximate
yes.
polynomial,
you don't have a sandwiching necessarily. And so this is a stronger notion because this is a harder problem. Right? And we will actually see that you need something stronger than approximation polynomials. Not necessarily the full extent of sandwiching, but at least approximation is not sufficient. Again, this works for any hypercontractive, D star, and gives new results for several classes. Because for these classes, the idea is that because this notion of sandwiching is important for pseudo-randomness, there's already bounds that for all of these functions that we studied in the context of pseudo-randomness. So we just use those. Okay. So what is our approach? Recall that for label noise, we said polynomial approximation can actually give you a very, very good hypothesis that competes with the best in class. And this is because due to polynomial approximation property. The concern here is that due to the contamination, there perhaps is no low degree polynomial that approximates a star over the input distribution, the input set of examples. So we have an input set of examples, but now it's not coming from an axis distribution necessarily. There is some contamination. So maybe the polynomial regression will fail. there's no polynomial that actually approximates f star. Instead, the general, morally, what we want to do is to find a filtered subset that respects the polynomial approximation property, but we want to do that by only removing a very, very small number of clean examples. Because if we remove too many clean examples, then we never take them into consideration, and maybe we make mistakes on them. So we only want to remove a very small number of clean examples and respect the polynomial approximation property. So the question is, can we do that? And actually, the stronger notion of approximation that sandwiching polynomials is actually helpful here. And it is helpful because of this very simple but very useful observation. So imagine you have this set S, whatever that is, and you take the empirical expectation over this set S of P up minus P down, the two sandwiching polynomials. If this is small, then P down approximates F star under S. Why? Because F star is always between them. So if these two polynomials are closed, then they're also close to F star under S. So what we did with this observation is reduce an approximation property with respect to F star, which is a complicated concept that it's a half space or intersection, so it's not that easy to argue about, to just a property about polynomials. We just need to preserve the expectation of this polynomial, P up minus P down. And then polynomial regression would work because this would give us for free approximation for F star, polynomial approximation for F star. Okay, and the challenge is to preserve this expectation of P up minus P down by only removing points that are very unlikely to be clean. Okay, so this sounds very, very, this rings a bell. So there are all these outlier removal techniques from robust learning that actually do exactly this, preserve expectations without removing a lot of inliers. But the catch is that many of these techniques focus usually on squared polynomials. Here we have a non-negative polynomial, P up minus P down, but it's not necessarily squared. So that's one nuisance. And the second caveat is that the bounds on the expectation that these algorithms achieve typically, it becomes worse as the degree of the polynomial increases. Here, both of these are problematic for us because the degree of this polynomial we want to focus on is correlated with this approximation quality. Okay, so if we want the expectation of P up minus P down to be epsilon, its degree has to be some polynomial or some polylogarithmic function of epsilon. So it turns out that these caveats lead to race conditions between the approximation quality and the degree, and these techniques do not apply out of the box. But this doesn't mean that we need to come up with something more complicated. We actually just need to be careful and even simplify the algorithm. Okay, so this is the algorithm for outlier removal. What it does is it says, okay, restrict your attention to polynomials whose absolute expectation over D star is epsilon. Okay, just restrict to those polynomials, and then find a polynomial among those whose expectation on the set, the input set that you have, is 10 times epsilon, the empirical expectation. Okay. Then find some threshold. Remove all the points x from the input distribution, from the input examples, such that the value of p of x is larger than some threshold, and repeat until you cannot find such a polynomial p. Okay, and the idea here is once you find such a polynomial, you know that there is a threshold upon which the number of outliers is more than the number of inliers. Why? Because, well, the absolute expectation of P under D star is small. Okay? So this means that P, the values of P are roughly close to 0, usually. under the D star. So the inliers will give P of X small values. But under the input distribution, the empirical expectation is very large. It's 10 times larger than the absolute expectation under the clean. And this means that there must be some points, adversarial points that give this polynomial large values. In particular, you can find a threshold P, tau, that if you condition in P of X greater than tau, the outliers are more than inliers. And therefore, you obtain these two guarantees. Once the algorithm ends, for any polynomial whose absolute expectation is small under D star, its empirical expectation over the filtered set is also small, but in the meantime, the algorithm only removes more adversarial points than clean points. Okay? So these are the two guarantees that are sufficient for our purposes. Let's see. So the first theorem is for bounded contamination, but it's not what I promised. Now I'm just saying that the sandwiching degree, if you have bounded sandwiching degree, then you have an algorithm for bounded contamination. This is like a warm-up. And how do we do this? We just use this theorem, but how will we use it? So we just apply the guarantees to the polynomial Q of X equals P up minus P down. Why? Well, we know that the expectation of P up minus P down, or its absolute expectation is the same, is small under D star. So under the filter distribution, the expectation will also be small. So that's great. And also, the algorithm removes more adversarial points than clean points. But the adversarial points are only a small number of points, or eta times n. So the algorithm removes eta times n clean points at most. So therefore, we have essentially found a subset that has the two properties we want. It respects the polynomial approximation property and contains almost all the clean examples. So polynomial regression works. That's the idea. But remember, we asked, when is efficient learning possible under heavy contamination? Okay. And the answer is, we can just use the same algorithm, the same exact algorithm. We just change one parameter of the algorithm. And this is, instead of going from expectation under clean being epsilon to expectation under the input being 10 epsilon, we go from expectation under clean being epsilon squared over q, so it's even smaller, to expectation under the input being 10 epsilon. Okay? So this means that every time we remove points, it's essentially the same exact analysis, but every time we remove points, now we remove q over epsilon times more adversarial points than clean points. So the maximum number of points, of clean points we can remove is epsilon. So we only remove a small number of points. Here we're just saying that we're much more selective, right? We only remove points if they do something very unnatural for some polynomial. And we pay for that because we require better approximation property for the sandwiching polynomials. Okay, so that's how we get the algorithm for heavy contamination. But we promised that approximate degree is sufficient. So that's the theorem we promised. We will show. And I'm claiming that the same exact guarantees will give us this theorem. The only thing we need to do is to apply these guarantees for the appropriate polynomial Q. So earlier, we had the sandwiching polynomials, so a natural choice would be P up minus P down. But now we don't have P up and P down, we just have P star that approximates a star. So what's the correct choice for this polynomial? Well, the correct choice is this. It's P star of x squared, P star is the approximator, minus 1. Why is that the correct polynomial? Well, this polynomial encodes a property of polynomial approximators of Boolean functions. And this property is that if P star approximates some Boolean function, then its square should take values that are very close to 1, usually. Why? Because f star is always 1, so f star squared is always 1, and therefore, if p star approximates f star, its squared values should be close to 1. So the absolute expectation of q of x is small, so that's great. And additionally, we need to be careful, and with some steps, some careful steps, you can show that that's all you need. The only thing you need is that the expectation of p star of x minus 1 is preserved. That suffices for bounded contamination. But it doesn't suffice for heavy contamination. Okay? And instead of going through the analysis to tell you why it doesn't suffice, I will just give you a lot of it. So, approximate degree does not suffice for learning under heavy contamination. Let's use the monotone functions class, which is my favorite class of proving lower bounds. Its approximation degree is sublinear, as we said earlier, but its establishing degree is known to be linear in the dimension. So what we show is that learning monotone functions with respect to the uniform distribution, even under 2 heavy contaminations, so 50% of the data are clean, requires exponentially many examples. Does anyone perhaps see why that is? So the reason is that when you have the adversary your monotone function could be either the all ones function or the all minus ones function. And assume you don't have assume you only have 2 to the d over 100 examples, right? Well, we know that what's the probability that 2 points in the hypercube are comparable? Meaning that all the coordinates are, satisfy the same order. Well, the probability is exponentially small. Is at most 3 over 4 to the d. Okay. So with very very large probability, any 2 examples from the hypercube, random examples from the hypercube, are incomparable, and therefore, if you don't have enough samples, the adversary can draw an equal number of examples, and they will all be pairwise incomparable, so any labeling will be realized by some monotone function. That's what monotone functions are. So if your function was the all ones function, which is monotone, then the adversary will label the minus 1, and op total would still, your error benchmark would still be 0, right? Because there is a monotone function that classifies everything correctly, because nothing is comparable. Yet, you don't know whether your function is the plus 1 or minus 1, and then your error is 1/2. So even though op total is 0, you need to pay for constant error. Yeah.
I'm slightly confused.
Yeah.
Initially, you said the sample complexity is just the
For VC classes, monotone functions are not VC classes.
Yeah.
It's not a VC class. So here it's important that we are under uniform distribution. So under uniform distribution, the metric entropy is different. Okay. So as a recap, for bounded contamination, we showed that polynomial approximation suffices. For heavy contamination, sandwiching approximation suffices, but polynomial approximation does not suffice. And there's even a separation between bounded and heavy contamination, even in terms of sample complexity. So it is not the case that the adversary can only help you information theoretically. Even information theoretically it can harm, but not for VC classes. And all of the upper bounds were given by the same outlier removal technique, which is inspired by robust learning. Okay. So just to give you some broader context. So I've been working on, I'm trying to give strong learning guarantees for efficient algorithms with weak or at least verifiable assumptions. So these are some problems I've been working working on, but let's just focus on two of them that are relevant for what we discussed here. Okay? So, testable learning. What is testable learning? So this was defined by René Rubinfeld and Arsène Vassilian, and there the learner is asked to, it receives some input and is asked to say, check whether the input is structured enough so that you can efficiently find the best classifier. Okay, so check whether the input is structured enough. Well, learning with heavy contamination is the finding version of this problem. It's asking the learner to find a subset of the input distribution that is structured. Okay, and for both of these problems, sandwiching suffices, but standard polynomial approximation does not suffice. And let's see an analogy. So remember in the very beginning, I told you that question one needs to ask when trying to provide provable guarantees for learning algorithms is how to model the input. And that's not trivial. Well, it turns out that even modeling how to evaluate the output of the algorithm is also a non-trivial problem. And this is the reason. Okay? So there's a misdistribution shift. So imagine you have labeled data from some hospital. You have the patient, medical records, and the outcomes of treatments. And there's a hospital B from which you only have unlabeled data, only the medical records, but not outcomes of treatments. So your goal is to decide correct treatments for hospital B by only using data from hospital A. This is a critical setting, so we actually need guarantees. So one question to ask is TDS learning, or testable learning with distribution shift. So the question is the evaluation distribution, the test distribution, from which we can only access through unlabeled data, is it similar to the one we have trained on? Okay, so that's the question of TDS learning. And the finding version of this problem is PQ learning. Okay, so this asks, PQ learning was actually defined before TDS learning. But PQ learning asks, find a subset of the test examples that are similar to the training data. So instead of saying the whole test distribution is similar, we're just saying these examples are similar to what we have trained on. And what we showed is that outlier removal can be used to extend results from TDS learning to PQ learning. So this is this is exactly what happened for for testable learning and learning with heavy contamination, essentially. So in fact, we first solved this problem, which is a new problem, and this motivated us to solve another problem, learning with contamination. Okay, so let me just finish with a couple of open questions. So one question, which I think is very, very important, is whether, so the outlier removal technique we had required, remember the first thing I said is, restrict your attention to polynomials whose absolute expectation under the clean distribution is small. Well, to do that, you need to have sample access to the clean distribution, only unlabeled samples. So if your your target distribution is the uniform on the hypercube, you just flip coins. So you can do that. But the thing is, if maybe there's another nice distribution that is in the training data set, and we would like to work with respect to that as well. So an open question is, can you actually remove that condition that you need sample access to B star, and instead have an algorithm that works universally over a broad class of distributions? And the second question is, under heavy contamination, can we obtain faster algorithms, but perhaps through allowing ourselves to have relaxed error guarantees? So remember, I said that for special classes and relaxed error guarantees, there's all this work that gives results for bounded contamination, and these algorithms are actually more efficient than the ones that achieve the best error guarantees. But can we do something similar for heavy contamination? question, and yeah, with that, that's